Hello everyone, I'm Joe. Welcome to my channel, and today let's talk about some basic concepts about digital logic. Let's start with some basic terms. First, signal. A signal is a physical quantity that varies with time and contains information. For example, I have two persons running here. We have person A and the person B. Okay, so if we plot out their speed as a function of time, basically we can get two curves. Say this is for person A, and this is for person B. So from those two curves, we can know that how fast each person is running at different time points. Those are information. Then we got two signals, signal A and signal B. Similarly, an electric signal is defined as a voltage or current that contains information. And the electric signals can be categorized into two big groups, digital and analog. The digital signal is a voltage or current that has discrete values. Discrete means whenever the signal needs to change values, they change instantaneously. Like there's no transition time or a period or transition period. Okay, it just change from one value to another quickly, from high value to low value, or from low value to high value. But for an analog signal, the voltage or current has continuous values, like a sinusoidal waveform, that's showing on the right. If we have a system using only analog signals, we call it analog system. If we have a system using only digital signals, we call it digital system. However, in reality, we rarely have a system using pure digital signals. In most cases, we have a mixed system instead. So on the left, there are two examples showing two different systems. The first one is a pure analog system, and this is basically an audio amplifier circuit, which can be commonly found in some inexpensive karaoke systems. So here's how it works. When the sound waves comes in, the microphone will detect the vibration and convert the vibration to analog signals. Then those analog signals will go through a device called a linear amplifier to be magnified. Finally, a speaker will convert the magnified signal back to sound waves. That's how we hear the magnified sound. The second example shows a CD player system circuit. In this case, the information is stored in a digital form. So whenever we want to play the music or sound from the CD, the information or the digital signals will go through a device called DAC, digital to analog converter, to be converted to analog signals. Then these analog signals will go through the amplifier and speaker to be heard as sound. So now you probably have this question, like, it's kind of obvious that the mixed system looks more complicated than the analog system. So why do we just use the analog design all the time? That will save some resource or money, right? So the reason is that there are kind of big advantages when handling digital signals than analog signals. The first reason is that the digital signals can be transferred and stored much more efficiently and reliably than analog data. Second, the digital systems usually consume much less power than analog systems. Finally, the digital signals are generally more robust to noise than analog signals. Because of those three reasons, whenever we want to design an advanced system which is robust and low power, we always prefer digital system. However, because in nature most signals are analog, so we still need the analog part there, but we only use it whenever we want to output our result. To design a digital system, we follow a top-down design flow. So first, you have to define the system you want to design. For example, say I wanted to design a CPU here. Then second, you need to break down your system into different blocks. That's what we call subsystems. Go to my example again. Say I wanted to design a CPU, then I need to break down my CPU into different building blocks, which by their function. For example, I need an ALU to handle the arithmetic and logic operation. I need many registers to store my temporary result. Also, I need a timing and control circuit to control each blocks. And I also need some I/O port control, interrupt control, and data bus, address bus, etc. So those are my subsystems. After that, we need do the logic design for each of the subsystems or blocks. In this stage, we will use the basic logic building blocks like logic gates, some circuit with or some logic components with specific functions like multiplexers, decoders, encoders, etc. Finally, after we determine our logic design for each blocks, we will realize our logic design using the basic circuit elements like transistors, diodes, resistors, etc. So this is called top-down design flow. However, for the system and the subsystem design and the transistor circuit design, those are beyond our topic here. So here we only focus on the logic design. We'll talk about the building blocks and about how they work and how to use them to build some logic circuit. So the logic building blocks talked in slides 4 generally have one or more inputs and one or more outputs, which takes on discrete values. In other words, digital signals. And those building blocks can also be categorized into two big groups, combinational and sequential. For combinational circuit, they are generally made by logic gates, and their outputs are directly determined by the inputs. However, for sequential circuit, the outputs are not just determined by the inputs, but also determined by the previous states of the output. So in another word, for sequential circuit, there will be a memory part that can remember the previous state of the output. So that's the main difference. Finally, logic levels. The logic levels is defined as a voltage range that represents a defined digital states in an electronic circuit. So we all know that the digital states basically means 1 or 0. There are only two states, which is corresponding to the binary number system. Right. But there are different ways to define the states 1 and 0. In positive logic, state 1 is defined as logic high or true state, and it's corresponding to high voltage range. State 0 is defined as logic low or false, which is corresponding to low voltage range. For negative logic, state 1 is defined as logic low instead, and also can be called false state, and it's corresponding to low voltage range. State 0 is defined as logic high or true state, and is corresponding to high voltage range. Unless specified for a given system, we always assume the positive logic is used by default. Okay, and to help you understand the idea of voltage range, let's look at an example here. So here I have two different digital systems using different power supplies. So the first system uses 5 volt, and the logic 0 is defined as any voltage between 0 to 0.8 volt. Logic 1 is defined as any voltage between 2 to 5 volt. So say we have 0.5 voltage. We add this voltage to the system, then it will be recognized as logic 0. If we have a voltage 2.5 volt, it will be recognized as logic 1, right? However, in the system on the right, because it has a 12 volt power supply, things are changed. Say we still add the same voltage. If we add 0.5 volt here, it will be recognized as 0 too, so no difference. But if we add 2.5 voltage, because the logic 0 for the second system is defined as voltage between 0 and 5 volts, so 2.5 volts still be recognized as logic 0. So that's the thing I want you to be aware of. So because in different system using different power supply, we still have 0, 1, 0 and 1, but their corresponding voltage range may change. If you found my video is helpful, please help like, share, and subscribe, and I will upload other videos gradually. Thank you.